so we just got done talking about probability distributions, and we know that if it's discrete data, we can list the probability distribution, like every possible x in the probability, but that doesn't work if it's continuous data, because there's too many options. And we talked about the binomial distribution, which was a specific type where you only had two possible outcomes, they were independent, and so forth. The next piece, we're going to look at a couple others. So today we're actually going to talk about two of them. We are looking at a probability density function, which is basically just an equation for finding our probabilities. Same things are true. We know that every probability has to be between 0 and 1. They have to add up to 1. If we are looking at it in terms of a graph, and we're graphing the probabilities, then it always has to be a positive, so you could never have a graph go below the x-axis. The first distribution we're talking about today, we are not going to see a lot of it, but it is the uniform distribution. So a uniform distribution is when every outcome is equally likely. So for example, suppose that United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So it could be at 10, which is like time 0, 11 would be x equals 60, or anywhere in between. Draw a graph of the distribution. Okay, so we've drawn some graphs before, and we were drawing like lines or dots on it before, but this one, if it's continuous, because we could agree between 10 a.m. 11 a.m., okay, anywhere in there, it's continuous. So we are going to connect it. So we'll start at 0. X is the number of minutes, so the maximum would be 60 minutes. And it said that everywhere in here is equally likely. So it is just as likely they show up at 10:01 as it is if they show up at 10:59. Okay, every minute is equally likely. So if the total probability is 1, and the length of this is 60, what is the probability for every minute? 1 out of 60. So my probability is 1 out of 60, and that is the same the entire time. So when we graph the uniform distribution, we're actually just getting like a rectangle. If I said they were going to show up between 10, 10, and 10:50, how long is it from 10:10 to 10:50? 40 minutes. So what would be the probability? 1 out of 40. So everything's equally likely, so our probability function just turns into a rectangle. The height is your probability. All right, so from this, find the probability of choosing a time between 15 and 30 minutes. So how far is it between 15 and 30? 15 minutes. Okay, and we're really just finding like the area of this. Now here's 30. You are between 15 and 30. You're somewhere in here, so it's really just finding this area. How do you find area of a rectangle? Length times width. So the length is 15. My height of this is 1 out of 60. So 15 times 1 out of 60 is 1/4. So 1 in 4 chance that they show up between 15 and 30 minutes. All right, this one, there is a 30% chance your package will arrive within the next blank minutes. So I don't know my number of minutes. The probability is 1 out of 60. And I know that if it's a 30% chance, that would be like 0.3. So how would you find x? Divide by 1 out of 60 or multiply by 60 and you get? So 30% chance they would show up in the next 18 minutes. All right. Any questions about the normal distribution, finding those probabilities? Or sorry, not normal, uniform distribution. Next one we're talking about is the normal. So we have seen normal distributions, we just didn't know that they were. We've talked a lot about shapes of things, and we were trying to decide if they were bell-shaped or not. Anything that is symmetric and bell-shaped is following what's called the normal curve. Okay, so we have seen like discrete data, so we had rectangles, but ideally the normal curve is continuous data, so we wouldn't actually have rectangles. With that, we know then the mean is the center, and you can add and subtract a standard deviation as you come out, and we know a little bit about our data. If it follows the normal distribution, so if it's bell-shaped, what percent falls within one standard deviation? 68%. Where'd you find that? The empirical rule. So the empirical rule applies here. 68% within one standard deviation. How many within two standard deviations? 95, and within three standard deviations? 99.7. So that empirical rule still applies here. I have just some properties of it. It's symmetric about the mean. So if it's a true normal distribution, the mean is the center, it's bell-shaped, so half of your data is above and half is below. Mean and median are the same. We have the area under the curve is your total probability, so that is 1. Empirical rule applies, and I put that empirical rule on here just as a refresher. So let's look at this one. Is this a normal graph? Yes. Is it symmetric and bell-shaped? Yes. Can you tell me what the mean is by looking at this? 2. What is the standard deviation? 3. How did you get that? When this graph is starting to flip out, that's our first standard deviation. So if 2 is the center, you have to add and subtract 3 to get to those. All right, let's compare a couple. Both of these have a mean of 10. Okay, if I look, that's where we have our highest point. One of them has a standard deviation of 3. The other has a standard deviation of 2. Which is which? Why? Okay. So the higher your standard deviation, that means the further you have to go before it starts turning outward. So A would have a standard deviation of 2. B, since it's more spread out, it has a higher standard deviation. So the more spread out your graph is, the higher your standard deviation. Interpretations, we can ask like what the area represents. We can think of it a couple different ways. It's either saying it's the proportion of the population with a certain characteristic. So if we have an area of 0.4, that means 40% of the population has this characteristic. Or we can think of it as a probability, like there is a 40% chance of this happening. So really all we have left is just kind of an interpretation question to finish up this piece off. If the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds, a standard deviation of 200. Draw a normal curve with the parameters labeled. So if I am drawing a normal curve, what does that mean? What's it? Bell-shaped, symmetric and bell-shaped. So we have the same amount on both sides, a peak in the middle. When I say the parameters labeled, that means the mean and standard deviation. So the peak of this has to happen at the mean, which is Alright, then the standard deviation, that's kind of when the graph starts turning outward. So that would be one standard deviation here and here. My standard deviation is 200, so what would I label this? And this would be, you would add and subtract your standard deviation. So part B says shade the area under the normal curve to the left of 2,100 pounds. So we will be eventually finding areas from this. So 2,100 would be here. So the area to the left would be all of this. Part C says suppose that that area is 0.3085. Provide two interpretations of this result. Okay, so we're writing two sentences. What does that mean? So this is the weights of giraffes. So it could mean, if we're looking at all of our giraffes, 30.85 had a weight less than or equal to 2,100 pounds. Okay, so or we could write it as a proportion if you didn't want to do a percent. So you can write this as the proportion or of our giraffes, 30.85% weighed less than 2,100. That's the first interpretation. What is the second interpretation? Okay, so you could talk about it on the flip side. We know that the total is 1. So you could also say then that means that 69.15% are more than this. If we're talking about our giraffes, how else can we interpret it? What else is true? So we can think of it as a proportion of the population, like describing our population with our giraffes. 30.85% are less than, 69.15% are greater than. Or we could think of it as, if I go pick a giraffe, the probability that its weight is less than 2,100 pounds is the 0.085. So you can use it to describe your population or for a probability here. Proportion describing the whole group or the probability for one particular giraffe. Questions there? Okay, so technically that is the end of section 7.1. We have quite a bit of time. We can either start 7.2 or you guys can get your homework done and probably have a little bit of downtime. Preference? Nobody's going to say anything? Let's do our homework first, and then we'll see how much time we have left, and we might start the next one at the end. So,